This video will demonstrate how to use the QCPA framework for processing an entire image. First, we need to load the image as a calibrated multispectral image. To do that, we can use the generate multispectral image function. And here are the options for that. I'm just using a standard visible image. It's a raw photograph, which I have here. The standards are in the same photo. I'll only be using the 7% standard, so I just put 7 in there. It's only a visible image, so there's no alignment required. I'll output the image as a linear normalized reflectance stack, and I'll call it flower. Now I just select the raw image here. This loads up the image and asks me to select the 7% standard. You'll notice that certain pixels have been highlighted here, and this happens where the pixels are overexposed. So on the petal here, the red channel, because these are dark red pixels, have just reached the saturation point. So it's just starting to be overexposed in the red channel. But because this is so close and there are so few pixels, this is still going to be fine for processing. You'll notice here though that the white standard is completely overexposed, so we can't use the white standard for normalizing this image. So I'll just select this 7% standard and click OK. And this loads up a linear normalized reflectance stack. Next, I need to select a scale bar in the image. So I'll select the line tool, and as you'll see here, for a scale bar I need to press S on the keyboard, and I know that the distance between this point and this point on my standard is 26 millimeters. So I'll press S on my keyboard and put in 26. Okay. This image is currently in camera color vision. That is, it's the normalized reflectance output for the camera's red, green and blue sensitivities. But we need to convert this into animal color vision for the QCPA analysis. So to do that, I can go Plugins, Micro Toolbox, Convert to Cone Catch. And I've already created a cone catch model, and you'll see other videos that describe how to create cone catch models for your system. For this demonstration, I'll be using this camera converting to human, long wave, medium wave and short wave spectral sensitivities. You'll notice this option to remove negative values and replace them with a very low value. The QCPA framework uses the receptor noise limited model, and that it cannot deal with negative numbers. So in order to get around the problem of negative numbers or zero numbers, we can replace them with very small numbers, which makes the framework work fine. This has converted the image into cone catch values. You can see here this is the long wave, medium wave and short wave channels. The red pixels here are highlighting where negative pixels have been detected and converted into very low values. When you have negative pixels in very dark areas of the image, it's not a concern at all. It probably means that the values are so dark that noise is creating values that just go into the negative range. But where you have negative values on very colourful parts of the image, you should start to consider that the colours might be out of gamut. They could be beyond the ability of your camera to model the colours accurately. It could be a problem with the modelling, it could be a problem with linearization, or it could be beyond the visible gamut of the receptor system. In this case, the short wave for humans. You'll see not all of the pixels are negative though. It's getting quite close in many areas, so it doesn't look like we have extreme out of gamut colours here. It's right on the edge, but it looks like it's still able to model them okay. The QCPA framework considers both chromatic and achromatic channels. Achromatic means a luminance channel, and here when we create a cone catch model we don't have a luminance channel yet. So here we have the long wave, medium wave and short wave, and we can automatically add a luminance channel using a specific tool that's been provided. So here if we go Micro Toolbox, Image Transform, Create Luminance Channel, it brings up an option to create a luminance channel at the end of this stack. Now for humans, it's thought that our luminance channel is the combination of long wave and medium wave. Our long wave cones and medium wave cones have their outputs effectively summed together, and that's what's sent down the optic fiber to our brain. Other animals will have other methods for creating a luminance channel. In birds, the most sensible thing to use is probably just the double cone system, and for that you'll already have the model will already output the double cone spectral sensitivities. For other mammals, it's perhaps most likely to be the long wave or medium wave sensitivity on its own. And in some other animals, it could be a combination of all three. So here, just for the human system, I'm going to make an average of the long wave and medium wave. And if I press OK, that has created this fourth channel in the image, which you'll see here is called LUM for luminance. At this stage, we can select which region of the image we want to process by cropping certain areas out if we don't want to include them. So, for example, I'm not interested in running the grey standard and its housing through the QCPA analysis. So I can select the rectangle tool and just select the region that I want to process. I can press Control Shift and X to crop. And this has created a cropped image with all of the cone catch values that I want to process. So now we're ready to run the QCPA framework. To do that, we go Mica Toolbox and QCPA, Run QCPA Framework. This will bring up an options dialog with the broad options of which aspects of the framework we want to apply. It's very flexible in being able to apply any of these functions independently or all of them together in one workflow. So first we can choose which type of acuity correction to apply. Acuity view works by processing using fast Fourier transform. So for that it requires a rectangular or square image. We've written our own version of a Gaussian convolution which can work with any shaped image. So if we have a region of interest, we'd be able to compare that objectively irrespective of the shape of the area that we're measuring. The receptor noise limited rank filter is used for reconstructing sharp edges in the image later, so we'll generally want to apply that, particularly when we're using acuity correction. Then we can select which type of clustering to use, if any. If we want to run the QCPA output options and do the full image analysis, we do need a clustered image, and that can either be done using our receptor noise limited clustering, so that's the agglomerative hierarchical clustering method, where we only need to know something about the receptor cone ratios of the receptor visual system. Alternatively, we can use the naive Bayes clustering method, and you can use this when you know exactly how many clusters you have in your image and what their average values are. But when we don't know, we should just use the RNL clustering. We can specify which visual system Weber fractions to use here. So these should match the model that we've just created. So in this case, I'm using humans, and the human values specified here must match the long wave, medium wave, and short wave values in the cone mapping model. We can specify the luminance Weber fraction, which is used in combination with the color, the chromatic Weber fractions to combine the color and luminance discrimination thresholds. We can choose the particle analysis, so that if you select the particle analysis, once the clustering has occurred, it will look at the shapes of those clusters and the distribution of those clusters and give a huge amount of output about them. And finally, we can select whether to run the local edge intensity analysis. This uses by default the output of the RNL ranked filter, so that's an image where the edges have been reconstructed following acuity correction. Next is taking us into the options dialog concerning the acuity control, and here we can specify the visual system acuity. You'll see on the website there's a list of lots of species where their acuity limits have been specified. For humans, we have an acuity of about 72 cycles per degree. I've put a a scale bar in the image, so it can use that, and we just need to specify the viewing distance, and in this case, let's say it's 4 meters away. Now I specified the length of the scale bar in millimeters, 26 millimeters, so we use the same units here. So in millimeters, 4 meters is 4,000 millimeters. Next, this is a very important option for rescaling. Mostly the images will be made smaller by rescaling, and that makes the processing more efficient. We definitely recommend rescaling the image to a certain number of pixels per minimum resolvable angle. This makes the processing more consistent between different viewing distances. We can also specify, when the Gaussian acuity control is used, specify whether to only measure a specific ROI, a region of interest, in the image. But in this demonstration I'm showing how to use the whole image, so we'll just leave that like that. This has created an acuity controlled image which is effectively blurring to remove any details that wouldn't be visible to a human viewing this flower from 4 meters away. But this blurring isn't particularly biologically meaningful or accurate. It's not what a human would be perceiving. We would perceive this flower as having nice sharp edges. And more importantly, for image processing, all of these intermediate gradients created at the edges, they confuse boundary strength measurements, and they make image clustering more difficult because of all these intermediate values. So we developed the receptor noise limited ranked filter to overcome this. It reduces noise in the image while also reconstructing sharp boundaries where they occur. Here you can choose how many times this filter should be applied, and you get limiting returns beyond about 5, so we'd recommend values of about 3 to 5 here. The radius that you choose here is very important, and it should probably match the pixels per minimum resolvable angle that we chose in the previous dialog. So there we chose 5 pixels per MRA, so we should put 5 in here. It slows the processing quite dramatically with higher numbers than this, and lower numbers will speed it up a lot, but might also mean that this filter isn't able to span the gradient accurately with lower numbers. The fall-off value here specifies the exponential decay fall-off. Values of around 3 are sensible. This changes the weighting of whether this filter should consider pixels that are closer in color to itself or further in color from itself. The RNL rank filter has finished processing the image, and you'll see this now has nice sharp edges at the boundaries. And now it's brought up the clustering options. So here we can specify the color threshold below which any two clusters can be combined if there are close enough color difference between them, and likewise for the luminance. Values of between 1 and 5 are sensible in these dialog boxes, but if you have behavioral data so that you know what values you should be using, that's obviously ideal. This is the number of loops. The processing tends to effectively finish after about 10 loops, but it doesn't really cost anything to have a few more than that. So by 20 loops you can be sure that the entire image has been processed. The radius multiplier specifies with each pass of the hierarchical clustering process how much larger should the radius over which the algorithm searches for similar clusters increase with each step. So a value of 2 means that it will start off searching for pixels with a radius of 1 pixel away. In the next pass it will look for clusters within a radius of 2 pixels, and then 4, and then 8, etc. Effectively increasing the receptive field of this filter as it goes. You can also specify a minimum cluster size in number of pixels. So this slowly is applied over every pass, so that by the final pass any clusters which have 10 pixels or fewer are forced to combine with their nearest neighbour. There becomes a point when it becomes more computationally efficient to, instead of searching for nearby clusters of a similar colour, to actually just compare every cluster to every other cluster in the image. This happens once the image is broken down to a few thousand or a few tens of thousands of clusters, which generally happens at about pass 6, but for a larger image you might want a slightly higher number than this. Here you can specify the number of clusters below which the algorithm should stop clustering, but we recommend this is just left at 1. And you can also, if you're interested in how the clustering works, output data from earlier passes, so you can see how exactly the clustering algorithm is working. You can specify your own label, but by default you'll see it labels the image based on the settings that have been chosen. So here we have the flower converted to human cone catch, we have the acuity and distance of the receiver, that the whole image is processed, and the Weber RNL ranked filter settings here, so the number of iterations, radius and fall off. So it's convenient to leave these settings in so that you have a record of all of them in your output. Here we can optionally specify to give us additional horizontal and vertical adjacency results for the QCPA analysis. And we might want to do this, for example, if we are interested in horizontal versus vertical patterns that occur in our images. If that's the case, make sure your images are always oriented in the same direction. So for example, if you're measuring an animal, that animal is always at the same orientation in your images. You can rotate your images before applying the QCPA framework to make sure that that's the case. You can also specify whether to output the adjacency matrix in case you want to do your own processing on the matrix. Now it's doing the clustering, and you'll see here it's giving information on how many clusters are remaining. With the clustering finished, it's showing us the options for the local edge intensity analysis. This analysis can be thought of as creating an edge map in the image, where the edges are based on the chromatic and the achromatic receptor noise limited chromaticity space. And so this model tends to produce values that are on something of a log scale. So for example, if we log transform the values of a natural scene, it will produce a fairly normal distribution of edges in delta S values. So using logs transform might make sense, but there's also the option to use no transform or a square root. You can also choose whether to ignore sub-threshold delta S values. So for example, if we put in values of 1 or 2 here, it would ignore all values that are below these thresholds. We can also choose whether to output horizontal and vertical data separately. So again, we might want to do that if you have specific interests in looking at the orientation of specific patterns in your scene. And this maximum display value, this is just for setting the viewing level, how bright the image should be. It doesn't actually affect anything in the analysis. So this outputs 2 images. The local edge intensity analysis is based on this output, the receptor noise limited ranked filter output, where the sharp edges have been reconstructed, but it's the unclustered image. This is probably the best image to use because it's controlling for acuity while also reconstructing these sharp edges, which is exactly what this method is sensitive to. Here we have 2 values. This one is the luminance value. It says lum here in the image title, and these colors show how intense the luminance edges are, and the color of the edges shows the orientation. Each of these images is actually a stack with 4 different variables in it, and you'll notice here this is showing us the first slice in the stack is the horizontal, and then there's a diagonal, vertical and other diagonal in the stack as well. So you can measure these independently if you want. And here is the same but for chromatic edges instead. So again, we can see that here is a very intense chromatic edge because the values are very intense. So if I go through the results, I'll close these windows as I go, but if you leave all of these results windows open and now go on to measure a second image, it will simply create another row and save all of your data without losing any data. So here are the results of the local edge intensity analysis. First we have the mean chromatic, so color, the mean chromatic edge in the image. So this specifies in delta S what the average is after the transform has been applied. And then we have the standard deviation and coefficient of variance. Then we have the skew and kurtosis. We might expect in a scene, in a natural scene with very random edges, we would expect a normal distribution of edge values. But in a scene where, for example, we have salient signals, like an animal pattern with salient bright spots against a fairly flat background color, we'd expect lots of very intense variables and then lots of very low ones. So we'd actually expect skew and kurtosis to be able to describe something about those values and how salient the image is. Then we have the same variables for luminance as well, and finally it shows us which transforms and thresholds we used. Then we have more output from the particle analysis. So this is showing us for each cluster, so for each different color cluster, it's being broken down into specific particles. So here, for example, color 1, so cluster 1 in the image, was actually made up of 6 independent particles, and this is showing us the location of those particles and different variables about its perimeter, the angle, and location of these different particles within each cluster. Here's a table showing the cluster results. So we can see that there were 7 clusters, and this shows us the area and the coverage. It's also showing us the mean values for each of the 3 channels plus luminance. And then it's showing us the receptor noise limited chromaticity coordinates for these values, and things like the Dmax chromaticity. So here, for example, for this cluster, the most intense channel was long wave versus short wave. This summary table shows us all of the interesting results of the QCPA analysis. So it's taken the clustered image and has run various image analysis methods on it. This is broken down into 3 broad categories. There's a huge number of different outputs here, and even more if we'd specified to look at vertical and horizontal separately. First we have CAA, that's the color adjacency analysis with lots of variables. Then we have the visual contrast analysis, VCA, and finally there is the boundary strength analysis, BSA. For more details on what exactly each of these parameters describe, have a look at the website or the appendix, where you'll find detailed information about what all of these numbers mean. Here we have the particle analysis results. So this is the average for each cluster. So rather than separating each cluster into its independent particles, this is showing us each cluster as one, showing us things like its area and perimeter length. Then we have the same cluster results for the whole image, which will be very similar to the ROI cluster results given we've measured the whole image. But if we'd measured independent ROIs in this image, it would be detailing each of those separately. You'll also notice here that the ROI Manager now has different numbers in it, and each of these numbers tell us which cluster is which. So these are output if we select the particle analysis, and if I select ROI 1 here, this is showing us where cluster number 1 is. And you can actually use this for selecting different parts of the image. So for example, the flower seems to be mostly described by cluster 4, 5 and 6. So if I select clusters 4, 5 and 6, I can actually combine these into one by pressing combine, and you'll see this has created a region of interest which is only the flower, and it's done that automatically. If we want, we can also create a false color image of any of these output images that we want. So for example, with this receptor noise limited ranked filter, I can go image visualization, make presentation image, and here if I, in the place of long wave, medium wave and short wave, have red, green and blue output, this will give us a nice color image for use in presentation and to just see what's happening in normal human visible colors. The clustering outputs this image as well, where each cluster is shown as a single pixel value. So the pixel value at each point in the image shows you which cluster it's been clustered into. So this could be useful for subsequent image processing. The clustering also outputs an average image map. So here each of the clusters has been converted into its average value for long wave, medium wave, short wave and luminance. So again, if we want, we can turn this into a presentation image. Image visualization, make presentation image, and red, green and blue. And here it's showing us the clustered color image. And finally, here was the initial image, which was blurred to account for acuity. And that's it. So that's showing you some of the an example of the QCPA framework, and you'll find much more information on the website.